Now we will look at the first result of this course, basic analysis, and it says that a sequence of real number or real sequence can have at most one limit. What this theorem tells about the uniqueness of limit. It does not guarantees that you always have a limit, but if there is a limit, then it will be unique. Before going into the proof, let's see what happens when we have two limits. So, suppose you have a sequence that converges to 2 points, say L and L prime, and these are not equal to, these are different actually, and this is L and this is L prime, both are distinct. So one of them will be smaller and one of them will be greater, and I can assume any one to be less. What convergence mean? That you get for all epsilon there exists a natural number such that all the term after that n, for all epsilon there exists a natural number n such that for all n greater than n, the terms after that this n will be at a distance at most epsilon from L. So suppose now you have two limit points L and L prime, and then you can find a epsilon which is half of distance of this. So this is the distance between L and L prime, and you take any epsilon less than this, then, and you are claiming that for this epsilon you apply this definition, then you will get a natural number n such that all the terms are inside this epsilon, all the terms are also inside this L, but this is not possible. You cannot get two different L and L primes and a natural number n such that all the term will go inside this ball and inside this ball as well. Okay, because they are distinct, they are far apart enough such that all the terms, if they go here, then they cannot be here. And this is the reason why this L and L prime to be the same. Actually this L and L prime has to be same so that all the terms lies inside this ball. Now let's jump into the proof that the sequence of real number are unique. I am not saying that they always exist, but if they exist, they are unique. And consider you have a sequence, call it xn, and xn converges to L, and also since it is uniqueness proof, so we have to take two things with similar property, and xn converges to L prime. Again, suppose you have a epsilon, let epsilon greater than 0, then there exists n1 for this and belongs to natural number such that for all n greater than n1 we have xn minus L less than epsilon. And also since the second sequence converges to L prime, we get there exists n2 for this same epsilon belongs to natural number such that for all n greater than n2 belongs to xn minus L prime less than epsilon. So again we use the trick we have learned that we can take n equals to maximum of n1 and n2, and for this n we can say that for all n greater than n, xn minus L less than epsilon, and also for this n, xn minus L prime less than epsilon. Consider L minus L prime. This can be written as L minus xn plus xn minus L prime, and this is equal to xn minus L, put a minus sign here, plus xn minus L prime, And by triangle inequality, we can write this xn minus L plus xn minus L prime, and we know that this is epsilon plus epsilon, so this is less than equal to 2 epsilon. The trick is this is true for all epsilon. This equation hold for all epsilon, or epsilon we can take epsilon to be 0, so this will lead to L minus L prime to be 0. We can make epsilon arbitrary small, and this will forces this term to be 0. So this implies that L minus L prime equal to 0, and this implies that L equal to L prime. And this is what we want to prove, that if you have two different limit, then they force to be equal.